Welcome. This is Professor Nathan Weezy of Marquette University. This is called Digital Control of Power Electronics, and in this section we're going to focus on the digital controller variant of a voltage mode control of a boost converter. So last time we left off, we had essentially designed a continuous time controller for our boost converter, and now we're going to convert this to the digital domain. And so a lot of the MATLAB code here is the same at the beginning because that essentially laid out our whole controller design. So for instance, here was our buck converter parameters. As we go down here, we're essentially defining the plant. And these are our controller design parameters. And this will be the controller design. So up until this point, this is all the same as the previous section. This is all in the continuous time. And what we're going to do is go ahead and actually take a look at converting this to the digital domain using two different transformations. And also we're kind of going to look at two different rates of sampling, okay, and just kind of see their effect on their system. So this, remember, let's recall that we had this boost converter switching at 200 kilohertz. So the first thing we're going to try here is a 10 kilohertz controller. So that means we're going to update or make our decisions or update the controller output at 10 kilohertz. In that case, it'd be every 100 microseconds. And what we'll do is we're going to design a couple digital controllers. So we're going to have the backwards Euler. So backwards Euler, that'll be line 5. And all we're doing is using the backwards Euler's approximation, line 4, and substituting that in for S. This min real is just to cancel any zeros or poles in the transfer function that MATLAB does not automatically cancel. And so this line 5 will give us a digital controller in backwards approximation. We'll also look at the variant from zero order hold, which we can just call C2D. It's a nice MATLAB function that'll give us that equivalent. With that approximation, we'll also do the Tustin, which is using that same function, just calling Tustin here, sample time at 10 kilohertz, and we'll have that design as well. So we got a couple of controllers to choose from. Now, not right away, but later on, I'm also going to consider looking at the controller at 50 kilohertz. That means we're switching at 200 kilohertz, so every fourth cycle we'll update our controller. Okay, and we're just going to see the effect of having different rates because it is going to change your controller quite drastically, and we'll see what that is. All right, so for the first response here, this is actually backwards Euler. And this is at 10 kilohertz. And this is our controller right here. Okay, it doesn't look too bad except for we have a big transient, and it doesn't look like it's settling down either. So the output voltage is constant, then we have our transient, and we're just ringing. And in this transient, just to be clear on what we're doing, we're stepping from 10% to 100% of full load. And you can see that we're oscillating. Essentially, this is not stable, so this is not good. And all I did was take our continuous time controller and convert it to digital at a sample time of 10 kilohertz and use the backwards Euler's approximation. So this actually illustrates that you can't just number crunch and assume that everything's going to be stable. So this is kind of here to highlight that effect. Okay, so let's take a look at now. This is Tustin at 10 kilohertz. Now you're saying, okay, this looks stable, but actually it is stable. It does converge down back to 10 volts after the transient, but this thing rings way more than what happened with the continuous time response. In fact, you can see here our discrete steps are quite large relative to the switching frequency. So this is our 10 kilohertz update of the duty cycle here. And you can see kind of these straight edge approximations of the current due to that. different rate between switching frequency and update frequency. So this rings quite a lot, actually. This is not a desired response, I would say. But just to kind of highlight that, you can't just arbitrarily pick a frequency here to do this at. Okay, let's go ahead and take a look now at this controller design. And what we are at now is this is 50 kilohertz. This is our controller for that. And this is backwards Euler. So I used the same one before as backwards Euler in terms of approximation, but now I'm doing the sample time at 50 kilohertz 5 times faster. And it's still 1/4 the switching frequency. So you can see here is the actual discrete steps in U. This is at 50 kilohertz, while the switching frequency here, which you can see in the current IL, is about 4 times faster. But what you can see here is that we're actually we got a better response. I wouldn't say it's the best response, but it's much better than anything we saw at 10 kilohertz. Okay, let's go ahead and look at now our Tustin at 50 kilohertz. And this is our controller here. And you can see a response here. And you can see this one's probably even better than the backwards Euler, but we're going to compare those all next. So again, you can see the right-hand plane 0. We start actuating up. The voltage keeps dipping. The controller doesn't know what to do because it thought that if you forward actuate, you'd actually bring the voltage up. So it starts swinging the other way, and then all of a sudden the voltage starts to come up again. Now that's again the right-hand plane 0 in action. But we do a good job of actually settling down at about 1 kilohertz here. You can see we're essentially in steady state. But we do have a second order response. That's to be expected in voltage mode control. All right, let's go take a look at all these on top of each other. Now I have 5 plots here. You can see blue is our continuous time. So that's the original one we designed in the previous section. Red is our backwards Tustin, which you can clearly see is unstable. Okay, so we can't just arbitrarily pick that. Yellow is our 10 kilohertz Tustin. So you see a big difference between Tustin and backwards Euler at 10 kilohertz. The Tustin actually stabilizes. The backwards Euler is just ringing. And then also you can see our backwards Tustin, our backwards and our Tustin at 50 kilohertz actually mimics the continuous time system pretty well. The only really major difference you can see is in delay. So like for instance over here, here's the continuous time, but here you see the delay in both the backwards Euler and the Tustin. And again, that's to be expected because you have a finite amount of time delay in a digital system. You don't actuate right away, but in continuous time, as soon as you develop an error, you're already actuating. So you can see the discrete differences there. You can also see the discrete differences. This is again 10 kilohertz, whereas in your steps for the 50 kilohertz are much smaller. Now what this is kind of showing, and this is not an end-all be-all for digital controller design for power electronics, but it's showing is, oh, why don't we just sample faster and faster and faster? Okay, yeah, definitely. I mean, the faster you sample, the better you're approximating continuous time to a point. Remember, you do have digital numbers that are representing these. You have fixed point or integers representing these numbers. So in general, you could get into, let's say you wanted to sample at the switching frequency. In this case, it's 200 kilohertz, but you want to design a bandwidth of significantly smaller than that. Let's say 1 kilohertz to 500 hertz. You'd actually have the same problem you have here with the backwards Euler at 10K. You would have this problem because you wouldn't be able to, essentially what you have is a bandwidth or a filter frequency that's significantly far away from your sampling frequency. So 1 kilohertz to 200 kilohertz is a 1 to 200 ratio, or even 500 hertz to 200 kilohertz is a 1 to 400 ratio. And when you get those large ratios between sampling and bandwidth or cutoff, that's where you can have a lot of problems, even without thinking about quantization or integer representation in your number system, etc. Okay, this it concludes the digital controller design for the voltage mode controller. Thank you.